Today we are parameterizing surfaces, and what's happening is that we are in the middle of developing different ways to integrate different things, namely the vector fields. We're going to integrate the vector fields. We've gone through a line integral where we integrated over a vector. We integrated a vector field over a curve, but now we want to extend integrating the vector field over a surface. So that gives you your extension for the line integral to this thing that we will call surface integral and flux. But for us to be able to do that, we need to parameterize surface. Personally, I think this parameterizing surfaces stuff should have been done early on when we parameterize curves, so that we can get a feel for how the parameterization works. But in this case, they decided to wait right before they actually need it, which I guess it's an okay thing to do, but that's what we're going to do. Yes? Yes. So I forgot to take my book out. Ooh. All right. So parameterizing surfaces. And the way we're going to start off thinking about parameterizing surfaces is maybe go back to see how it is to parameterize a curve. And we'll look at parameterizing curves in a couple of different ways, and then we'll see how that extends to the idea of parameterizing surfaces. So I'll start off with a recall statement. When we parameterize a curve, what we're essentially doing is we're creating a function that takes in a scalar as an input. That's your parameter t. And we often called it R, where R takes in a real number, and that's your parameter, and then it sends you to either R2 or R3, and then that draws out a curve in 2 dimensions or 3 dimensions. So let's go to 3 dimensions just so we're there already. And then we can look at R in a couple of different ways because it's a parameterized equation. Parameterized function. We can look at R as being defined vertically or with the vectors x of t, y of t, z of t. And then these are functions, but we usually look at them as objects, as geometric objects. And as we've seen in line integrals, we actually need to make this parameterization because we want to describe the object that we're integrating over. In those cases, we're integrating over curves. And a picture that we don't really talk much about is the domain versus the range of this thing. If we were to try to draw this all at once, when I say all at once, I mean with the domain and the range involved, that looks like it's going to amount to 4 dimensions, right? So what we normally do is we just look at the image of this in 3 dimensions, and whatever that curve might look like in 3 dimensions, it's just going to be the image of the curve. What we don't see and pay attention to too much is that this really comes from another axis, a t-axis, where by going through this t-axis and this interval in the t-axis from A to B, you're actually drawing out, the curve from the starting to its ending point. So from R of A to R of B. Is this making sense so far? Look kind of vaguely familiar? We do have a special case of this. And the special case is that let's go back to 2 dimensions here. If we have a graph already, graph y is equal to f of x. If we have a graph already that can be described as a function, y is a function of x, then instead of just redrawing this t-axis over here and calling it a t-axis, we just kind of end up replacing this with a t, and then replacing this with a t, and then that's your parameterized function. Do you know what I'm talking about? If I want to parameterize y is equal to x squared from x going to from 0 to 1, for example. If I want to parameterize that, I can just write this as x is equal to t. That's changing your independent variable as the parameter itself. And then your y is equal to x squared, but we replaced x with t, so now we're going to call it t squared. And then now this r of t, combination of x and y here, this r of t will actually draw out the same exact curve where your x is equal to t. Okay? So that's just a recap of parameterizing things. And we can throw examples. We know how to parameterize lines. Oh, God, I hope you know how to parameterize lines already. And then we know how to parameterize circles. Okay, so those are the 2 most important curves to parameterize. And then if there's any more complicated curves, they should, relate it to something that we deal with functions and stuff. All right. Is there a question?
So do you always make x equal to t?
If you have a function that's kind of where you have x as a function of y, then you might want to switch that way. So it depends on the situation. So we don't say always. I was going to say we never say always. But it's like saying always, not saying always. So.
What I don't get is why is it different than saying x equals x and y equals y?
You could do that too, but depending on how things are, we're so used to having, when we say parameterize a curve, we're so used to having t, so we just use t. But you could certainly use x if you want. That means in some of those line integrals that we have, instead of integrating with respect to t, we integrate with respect to x, which is still manageable. Okay? So the names of these, that's a good point. The names of these variables don't matter. They're like the integrals. They're dummy variables. Okay? In fact, we'll see that a great deal when we start taking a look at surfaces. So, parameterizing surfaces. Well, I guess we could just jump into it. So to parameterize surface, we're going to need 2 variables. So instead of just having one variable t, we're going to have to introduce another variable. So we can say t and s. Speaking of, doesn't matter what the letter is, we can use t and s. Most likely, a lot of programs use u and v But when we decide that we want to parameterize with respect to polar coordinates, we might want to use r and theta. Or when we decide that we might want to go spherical, then we might want to use phi and theta. So it really depends on what you're dealing with. But I'll try to use whatever is appropriate, and we can just say that we can always change it back to u's and v's if we had to graph it or something. All right, so given our special case down here from your curves, let's start with a special case for surfaces. Suppose you had a surface z is equal to f of x, y. You know how that looks like, right? And when you have a surface, a lot of times in these, especially with these integrals that we're dealing with, we want to restrict it to a specific domain. So we'll restrict it to a specific domain. Let's just, to make it easy for ourselves, let's look at a rectangular domain. So just like the curves, a lot of times we usually just want to restrict it to a specific length of a curve. We don't necessarily want the curves to go on forever. We have limits for t. So the same way we'll have limits for x and y. I was going to put x1, but let's use a and b, c and d. I'll get some nicer pictures for viewing purposes. Pictures that I'm drawing are for note-taking purposes, so you can take notes. Because if I pull out, graphing programs, it's hard to draw those things, right? So we're looking at this piece of a surface here, and we would be interested in doing something like maybe integrating over this surface, or maybe just finding the surface area. Okay? So in doing so, we want to, quote, parameterize this. And so let's parameterize this. And to parameterize, like I said, you need two variables, and because this is a special case where it's we're parameterizing off of a graph, we're going to introduce our two variables, x and y, as x and y. Now, I don't know what the book uses. I don't know if they use R. We use R. I'm not going to use R, but we use R to parameterize curves, so I don't want to use R here. I've always used capital phi. That's okay. What's the book use? They use R, of course. I don't want to use R. So you can use R if you want, but I'm going to use capital phi to parameterize surfaces. And so what we come up with here is a vector. Now I can write this vertically or horizontally with brackets, and I'll probably most likely be writing these things straight across, but once in a while if I write it vertically, don't get thrown off. Vertically is in X, Y, stuff like that. Well, I'll write it vertically today. And so, because the X is the X and the Y is the Y, there's nothing to change or nothing to do here. And I'll just keep my X as X and my Y as Y. And then my Z value, since Z is equal to f of xy, then that's what I'll put in for f of xy. Or that's what I'll put in for Z. So whatever that turns out to be. And then that's it. This is my parameterization for this. Yes. Really quickly, though. Right.
So this is where you said you use any
Yes.
RMs or whatever.
Yes. So, in fact, if I were to take out my 3D plotter with my newly updated Java, then this would look like instead of X's and Y's, I'll have to use U's and V's because that's what they use in that program. And then that now will change the way this looks again. It'll be U in the X, V in the Y, and then F of U, V in the Z component. Okay. So let's come up with an interesting surface. Not interesting. Let's come up with a boring surface. So, as an example, for example, let's say Z is equal to, yeah, Nisa. No, I don't want a specific function. I just want it to be vague. I mean, arbitrary. Vague is not a good word to use in a math class. So let's come up with a function. Cone, sphere, semi or hemisphere. What do you guys want? Cone. I think it's square root of x squared plus y squared. All right? So let's parameterize that. In fact, let's just go straight to our graphing program. It's not open yet? It's open. It's open. Here it goes. So for this particular program, if I want to parameterize a surface, I'll need to get this parametric surface out. And if you notice, the variables, the parameters are u and v here. And so like we said, we're just going to keep x to be u, and then y to be v. And then here we have the square root of x squared plus, oops, I just said u and v, right? U squared and v squared. And, I didn't specify the domain. Let's just go from like -2 to 2 or something. -2 to 2. We'll talk about this in a minute. For now, I'm going to put 10, and then I'll talk about this because this steps for you is a good visual for what's happening when you're parameterizing these curves. The steps tell you how many times to compute it along the y, along the u, and along the v. All right? That's not a very satisfying looking cone, but it's the cone. So deal with it. All right? Along the x, this is my x-axis. Along the x, I'm saying that I want to break this down to x steps, right? So let's exaggerate this and break it down to 50 steps. What do you think is going to happen? What? The squares are going to be smaller. Almost. What? Narrower along the x. So that not just squares are going to shrink, but just the x measurements are going to shrink. So it's not actually going to look like squares. We're looking at, actually, if we look at it straight down, you can see squares. But now, if we change just the x are going to have more cuts. Okay, so let's graph it. Looks like the y has more cuts. Really? All right, fine. So the x has more cuts. So now it becomes rectangular looking. Your grids would look like that. Still a cone. Now let's go the other way. Instead of, I guess this is refining your graph, making it more refined. Instead of refining it, let's go the opposite way. What if we break this down to like 4? So now you have this. It's wider, right? In fact, let's do 4 for the other one too. So it looks a little bit less like a cone. And the way these graphing programs work is that they use this information here, how many times, how many steps. They use that information to just draw points. And then they connect the points and make little surfaces out of them. And here, we can actually count that there are a total of 16 to count that. So there's a total of 16 pieces of planes that they computed, that they drew based on those points that they collected. Yeah? Yes, it's exactly the t-step in your calculator. You know, when you draw a graph in your calculator, they talk about the t-step. So how many steps, and then they're just going to take those steps, figure out the points, and then they connect the dots. So if you really zoom in, if you really take a look at your calculator's graphs, they're really a bunch of straight lines that are connected. It's just that how far apart are those dots so you're connecting that line. So that's how all graphing programs work, unless you start going to Bezier curves and stuff, and that's a different story. But even then, drawing it would be lines. Anyways, you get the picture. So this would be our version of getting a graph, or being able to graph this thing. So our domain is the XY plane. Our domain is just that flat thing. Say I wanted to, maybe this is a little too soon for this exercise, but let's say I wanted to draw that flat plane that this has a shadow over. Any ideas how I can parameterize? I mean, a plane is a surface, right? Even if it's just laying on the XY plane, that's still a surface. If I wanted to draw that surface, how would I parameterize it using this parameterization that we have? Any ideas? Put 0 in for z. What are we going to put for x and y? U and v. That's so obvious that you don't want to say it. U and v, duh. I mean, you're correct. Good job. No, yeah, I mean, that's how you do it. So this is our second parameterization here, where we're just looking at parameterizing just on the XY plane, and z is equal to 0 on the XY plane. And if we're all, if it all just comes from that rectangle, from -2 to 2, -2 to 2 in the x, -2 to 2 in the y, then this is what you get. Okay. So let me take this one out and keep this one here and take a picture of this cool drawing so that we can put it in our notes. I guess this needs to go too. Oops, sorry. Too many clicking things here. So if you guys have time, to go and mess around with this particular program, you should really, try to draw some cones and other things. Paraboloids, hyperboloids, those are things that we know of, and then try to look up some other interesting things to draw. All right, now when it comes to this, for example, this particular cone thing, when we have a problem like this, a lot of times we don't. I think I talked about this issue one time already about these things going off on the side, and you know how that happens, right? Why does that happen? Because of our domain. Our domain carries these things all the way up, and that's a lot of times when we have an application, when we're doing these surface integrals, what we're interested in doing is we're actually interested in cutting it on top, and in which case your cone would look like this, which looks more of a cone, looks more like a cone, right? So what we might be interested in doing is that our original parameterization with an x and a y gave us a square domain down there, so we might not necessarily want to always do it like that. So we could try to parameterize this a different way, and we can parameterize it using our polar parameterization. So our cone z is equal to the square root of x squared plus y squared can transform into a polar coordinates, or I guess since this is three-dimensional, we should technically call it cylindrical. So maybe we can consider a cylindrical parameterization and see how this would work. Well, how would that work? That would work, we need an x and a y, and z is equal to x squared plus y squared with a square root on top. Now, if we're going to go cylindrical on this, we're going to need to change the x into what? With an r. And then the z becomes just r. So what is this? What is this? This is your parameterization, right? Back to Ryan's comment. Can we just use the x and the y? Well, you can use x and y, use v's, r's and thetas. You can use r and theta as well. So if I were now to pull out that graphing program, and instead of, where's that other one? Why don't we just clear it all? This is number 2. Where's number 1? Can I access graph number 1? Yeah, but there's kind of something else that's happening. Damn it, Caesar. Yeah, there's something else that's happening when we do these surface integrals. And either that change of variable is built into the parameterization, or that change of variable will happen when you actually change a variable in your integral. And we'll see that when we get to the integrals next time. All right, so I can't seem to access surface number 1. This is surface number 2 here, because I closed that window, but I can't open it again. Can I? All right, so if we're going to want to parameterize this using r's and thetas, I'll just pretend that u is r and v is theta. Or I could switch it around if I want, but I'll just say u is r. So this would be r times cosine of theta, right? And then we have r times sine of theta. And then this is just plain old r, which is u. And now we want to make sure we adjust the r's and thetas here as well. So r goes from, yeah, we want to go from 0 to 1. Let's go to 2 for now, and then we'll see how that will play in. Actually, I don't want to go all the way up to 2. I want this cone to stop at 2 on top. So what does r have to go from? Think about it. All right, let's put 1, whatever. And then if we want this to go all the way around, we'll just go all the way to 2 pi. And you can adjust this and play around with this. Again, you playing around with it would be a lot more helpful than you watching me play around with it, because math is not a spectator sport. I didn't go all the way up to 2. I want it to go all the way up to 2. Should I put 2 here?
That was a total trick question.
Oh, I didn't think it was going to go all the way up there. All right. What's happening here? What's different about this graph? I guess we can take a look at the other graph. The other graph looks like this. What's different about this graph versus this graph? Take a peek inside. They're not rectangles anymore, right? They're trapezoids. And ideally, they wouldn't be trapezoid. They would be like sector parts of the circles. But unless we can refine it a little bit. Remember the refining business? Yeah. So let's try changing a v's. You want to make this higher or lower? So let's go to 50. 1? I don't think 1 will work. I think 2, 3 would work a little bit better, right? 4 would start taking on the shape of the cone a little bit more. And you can see this is the number of times we're going around in that circle. Now, if you're going all the way up to 2 pi, you're cutting it in 4, then you're looking at quadrants, right? And so if you cut it in 5, you're looking at splitting the whole plane into 5 angles. And so that's what's happening. So if we want to get crazy and go to 360, you can almost see the degrees here. Each of these would be a degree, and that would be about as fine as the cone can get. By fine, I mean refined. Oh, look at that cone. It looked like 50 was okay, so let's just go with 50. Don't want it to be too fine. And the steps for u, what do you think is going to happen there? What if we take 1? Because u is just a radial distance, and because this is a cone goes from one point to the other kind of as a straight line. There's no curves in the middle. It's just a cone, so that's all it's looking for, and that's exactly what you would get. If you start adding more numbers here, you'll see how it's going to start splitting up. 2, 3. It doesn't make it more fine. Yes, because of the fact that it is a cone and it is straight lines going up there, you're not going to get anything new by refining the cuts.
So if you actually had a sphere instead, and you 2 steps for your R, it would be like a dot, like a.
Yes.
Yeah. Okay. Like. The way it would be like a bend. Like
right.
A diamond, like a three-dimensional diamond.
Right. What's that? Yeah. So well. The thing about the integration part is that since we're not going to do the Riemann sum business, this is essentially playing into the Riemann sum. But if we're going to go straight to the integral and we know how to integrate, then it doesn't matter. These steps won't matter for us. They're just for eye candy. Yeah.
Why can't you just parameterize it as R equals R, theta equals theta, Z equals R?
Because
if you didn't have those specifications of X, Y, and you had R, you know what I mean?
Because what we're doing is we're graphing this in the Cartesian coordinates. Okay. And so we need X, Y, and Z and the relationships with X, Y, and Z. Okay? Now, if I wanted to graph the shadow of this, what's this parameterization going to be? Just put a 0. That's what she said. So if we take that same parameterization and just put a 0 here, and we have to make sure that we're matching with the limits for the U's and V's and stuff. And then we'll see that shadow on the XY plane. What happens if I change this number to what should we change it to? 2. -4. So now the cone is covered. What? Oh, seriously, we're going to want to do that. We're going to want to cover things. If we take the cover out, this surface has a boundary. If we cover it, the surface does not have a boundary. What? Yeah, so this here is a closed surface, and if you have a closed surface, then it has no boundary. Right? If I take that surface out, now it's an open surface and has a boundary. You wouldn't call it you wouldn't call it a boundary because it's closed there. If there was a hole there, it was punctured, then it would be a boundary. But if we're not saying anything about puncturing a hole anywhere, then we're assuming that the bottom of this cone is a closed surface. Well, let's talk about this hole. I mean, let's talk about this boundary. This is an open. So now, if I don't cover it, right, we have an open surface. And when I say it's an open surface, it has a boundary. Where's the boundary? It's what? The what? The rim of the cone, right? That's the boundary. Does that make sense? So if there's no cover for this, we have a boundary. Now, that boundary, Ryan said, it was the rim of that cone, the rim of that hole, is what he said. Rim hole. So what is, how would I describe that boundary? Tell me about that boundary. What? Yes. Okay. That boundary is a circle. Brian just said it was a circle. No, that's not a boundary because there's no hole there. Right. So let's keep this train of thought going. The boundary is a circle, right? Now, how can I draw that circle in this program? What do I need to do? What is that circle essentially? It's a what? A trace of a what? No. How would I draw that circle? A change in the z. A little bit more than that. That's about 10 seconds. Got something?
You mean like as a space curve?
Yes.
Oh, okay. Okay.
So, as a space curve, I want to, we're going back to parameterizing curves now. We're parameterizing surfaces, but we have to know how to do surfaces and curves. I want to go back to parameterizing this curve. How would you parameterize a circle that's been lifted up here? I have my parameterization template ready. What am I going to put? Tell me. My parameter is t, only one parameter. Two? Two cosine t, 2 sine t, 2? Just 2? Just 2? Just 2. Limits? 0 to 2 pi. Can you see it? It's on the rim. All right? So let's think ahead. Fundamental theorem of calculus. The integral of a derivative is one integral less. All right? Think about that idea, one integral less of the function. So what we're going to do is we're going to go up to a surface integral where we're integrating over a surface. So if we have a double integral, a surface integral of a derivative of something, we're going to go down to one integral, which will end up being a line integral over the boundary of that surface. No, because I'm going to, that's a few sections from now. And that's a lot of words, too.
That's the pure line integral and not path integral?
Yes. Okay. All right, so what I really wanted to get out of here in terms of what I want to put in your notes is just this picture. So let's take a picture of this and put it in our notes. Boy, it's hard navigating. They pop up these windows, but they don't close. Oh, then that would be a different story. When you have things that are undefined, you're integrating over them, there's a lot of other things that happen. Lisa. So what's happening with the shift? What if we shift it? How do you want to shift this? So let's take a look at our cone parameterization again, and let's shift it somewhere. I don't know where. Where do you want to shift it?
-2 on the x-axis.
-2 on the x-axis. Where's Mike? This is the cone? This is the cone. All right. So just like a shift, right, in regular graphing shift, when you shift, we're just going to add or subtract some constant somewhere. So Brian wants to shift this -2 in the x-axis. Sounds like we're going to put a -2 somewhere.
No, it's like u is equal to sine b. You're in the x-axis? Yeah, so then it'd be percent b -2.
Whoa. So this is the x-axis. Let me put the x-axis going towards you without messing this up too much. I can't. All right, this is the x-axis. So -2, that means we just move this back here so that the point will go back here, right? Let's see if that happens. Yep, there it goes. Oh, left the circle there. That's okay. All right. So we're going to need to be able to shift these things as well. And so shifting this way is good. And then to adjust the circle and make it follow it, again, we just probably need to throw a -2 in the x. Whatever x is already there, put a -2, and then the circle will shift as well. Okay? Is that shifting okay? Boy, I'd like to get rid of this circle right now. Space curve. Remove. Done. So let's might as well take a picture of this as a shift as well. Ah, go away. So the cone shifted by putting a -2 in the x direction. So we got a shifted cone. Okay? Maybe. Let's make the cone go sideways. Well, usually when you make cones go sideways, or any other figure for that matter, when you make it go sideways, we usually have an equation for that. So would you know what the equation is of this cone? Let's say your cone. Should we shift to or just do a? So let's make it open up along the x-axis. Yeah, so it'll be x equals square root of the other two, right? So it'll be x equals the square root of y squared plus z squared. And now if you just shift all the functions this way, so instead of r being instead of x being r cosine theta and y being r sine theta, maybe you might want to let y equal r cosine theta and z equal r sine theta. And then that's how your shift is going to happen. And x equals r. So x is equal to, and should we go r and theta, or should we go straight to u's and v's? Let's go r and theta. I think it's easier to think about it that way. So y is equal to r cosine theta, and z is equal to r sine theta. So this is your parameterization with u's and v's. And then you'll see it sideways. So let's graph it. So x is equal to just r, which is what we're calling u, and this is the cosine, and this is the sine. Yeah, maybe. I need to tell you another story about surfaces. So here's your cone opening up towards the x. Okay, that was neat. Let's try it. What do you think will happen if we put a negative in the u? It'll open up towards negative x-axis. Let's see. Oh, there it goes. Okay. Again, be a lot better if you guys were doing this yourselves instead of telling me what to do. Okay. Doesn't matter whether you put the sine here or the cosine there. Doesn't matter. It draws it out. It looks like it's the same image, right? What do you think happens, though, when you switch those two things? Let's starts with positive. If we want to look at it a different way, let's look at the curve, right? So if we take a look at the curve, x equals sine t, y equals cosine t. So I usually, when I write this down, I usually have the x have the cosine and the y has a sine, right? So if I switch this and I say my t goes from 0 to 2 pi, what do I have? Well, I still have the circle. But what's different about this circle compared to the other circles that I've had? As a starting point, more importantly, it goes counterclockwise. We usually want it going counterclockwise, but this is going to go in the clockwise direction. So when you switch the sines and the cosines around, it might still draw the same thing, but then your orientation is going to change. If you have a surface, what does an orientation mean? So this is for curves. This is C-U-R-V-E-S. For surfaces, when you parameterize it using, I'll go back to the cone going up, r cosine theta, y is equal to r sine theta, and z is equal to r, versus switching the x and the y components. Maybe I should do this other one in a different color. What's actually happening to your surface, I wonder? So being drawn differently, right? This whole idea of being drawn differently. Your surface is still a surface. And so when we talk about an orientation for the surface, we talk about, how should we put it? A normal vector coming out of the surface. So when we talk about curves, we parameterize curves, and then what we have when we parameterize curves are tangent vectors, right? Just the derivatives. Over here, when we parameterize surfaces, we're drawing it a certain way, and I didn't draw this picture earlier, but maybe I should have. We're drawing it coming from a domain. Okay, maybe I need to talk about the domain business a little bit more. I got carried away with just drawing the graphing program and stuff, and I forgot to talk about the other stuff. So let's reel ourselves back a little bit. When you're parameterizing surfaces, what you have is an output of a surface. This is your surface, right? But if you parameterize it not using the X and Y parameterization, if you use it using like polar coordinates or cylindrical coordinates or some other weird way to parameterize it, what's happening is that you're really coming from a UV axis. And hopefully your domain is a nice simple rectangle that maps this space into this surface. Okay, this is, I'm going to go back to the beginning. This drawing that I just had is similar to this business where you have a t-axis and then you have a resulting curve in 3 dimensions. Okay? So now I'm trying to make this parallel to a parameterized surface where you have something that comes from a UV plane to something in 3 dimensions, a surface in 3 dimensions. So really what you have here, if I want to use my notation here, what you have is this function, this parameterization that I have, takes something from 2 dimensions over to 3 dimensions. And in terms of those rectangles, you know how the first one had squares and rectangles and then the other one had regions of a circle? So what's happening is that this little portion of your domain will get mapped into this little portion of your domain. And then if we refine the U's a little bit more, then you'll have more refined cuts in the one direction versus the other direction. Okay so far? All right. So here's the heart of this story. To understand the orientation of this, when we talk about an orientation for curves, it's simple because we just follow the curve and you look at the direction vectors, the tangent vectors. You look at the derivatives, right, the tangent vectors, and that they tell you which direction you're going. And it's a one-dimensional object, the curve is, so you can only be going forward or backwards. There's only 2 directions. It turns out for surfaces, you can also be looking at 2 directions, strangely enough. What happens is that your U and your V, you can think about this as delta U and delta V business. And what happens is that these vectors over here that are coming from the UV plane get mapped into the surface over here as tangent vectors. Okay? Is that okay so far? If I were to take this vector over here and map it using this function, then I'm going to get that tangent vector. That actually comes from Let me do the blue one first. That blue vector over here, when it gets mapped over here, it's actually coming from taking the derivative of this parameterization with respect to u. Now we have to do partial derivatives. It's not just r prime of t, right? X of t, y of t. Now we have to take a look at this in pieces. And then the red vector is the derivative with respect to v. So these vectors over here, we can think about these vectors as the derivative of this transformation. Okay? So there's two things that we can compute out of these two tangent vectors. One thing, really. Well, two things. If you see two tangent vectors sitting on a plane, sitting on a surface like this, what do you feel like doing to them? You feel like, me too. So you can cross them. What happens when you cross a couple of vectors? What do you get? A normal vector. Okay? So now imagine if you switch two of those components, the x and the y. What do you think might happen? Didn't wait for 10 seconds, but yeah, you get the normal vector going the other way. Okay, that is going to determine your orientation. So, say it again. No. I don't think there are names for that. So when they describe the orientation of your parameterization, you can say it's your normal vectors pointing downward or upward, or if there's a definitive inside and outside of a particular thing. Well, if it's closed, then it's clear that there's an inside and an outside. If it's open, inside and outside isn't so clear. But there's two sides to a surface, right? So in this particular orientation, one orientation might have you going outward, and then another orientation might have you going inward. And so keeping track of your orientation will be important, because orientation is going to be one of the keys when you're doing a flux integral. The problem will probably tell you. And if you have it oriented the opposite way, it's off by a negative sign. Just like in line integrals. If you wanted it oriented going outward, and then for some reason you gave a parameterization that made the orientation go inward, you can go through with the same calculations and then just put a negative sign in front of it. So you have to keep track whether your orientation is orientation preserving parameterization or orientation reversing parameterization. There's a name for that. OPP? very few people that get that joke now. How many people know what she was talking about? So, old school rapper jams and stuff. Orientation, preserving parameterization. Orientation, reversing parameterization. So you can label your parameterization as OPP or ORP, and then if it's OPP, you evaluate your integral the same way. If it's ORP, it's reversing, so you just throw a negative sign in front of it. Okay? Now, surfaces generally have two sides. And so having an orientation is clear when you have a surface. And if you have a normal vector that's pointing out this way, the only way you can get to the other side is to cross an edge to get to the other side. Why is that funny? Is it one of those obvious things again? Well, duh. You have to cross an edge to get the orientation to go the other way, or to get the other normal. Okay? So these are called oriented surfaces. The edge, I mean, if it's a closed surface, then the way to get to the other side would be you have to actually come out to get to the other side. It's not like a smooth thing where you can just get to the other side. So anything that this has this is a can that has an inside and outside. So my normal vectors here. The only way I can get my normal vector to point the other way is that if I go onto the other side on the inside. So this is an oriented surface. It begs the question, is there a non-oriented surface? If there is, we're not going to study it. So the sphere, if it's a closed sphere, the way to get to the other side is you have to actually get through. If you cut the sphere a little bit and get to the inside through an edge. Oriented surface. So is there a non-oriented surface that you can think of?
Wait 10 seconds.
Running out of time. Ran out of time. So a Mobius strip is an example of a non-oriented surface. If you look at a Mobius strip and put a normal vector on one side, you can just go along the strip and eventually you'll get to the other side without crossing over the edge. Okay? So fortunately, we're not going to be studying Mobius strips or non-oriented surface. All our surfaces will be oriented, which means you really do have to keep track of your OPP and ORP. So why did chicken cross the Mobius strip? To get to the same side. All right. One more thing. I said there was two things to compute with these two vectors. One of them is to cross them to get the normal vector. What's the other one? No. It's along the cross product. It's doing something else with the cross product. No. What's the magnitude of the cross product? What's the magnitude of the cross product give you? Area of the parallelogram. That's how we're going to find the surface area. We'll do that next time.